August 14th, 1945, 09:32 hours, Aberdeen Proving Ground, Maryland. Major Robert Harrison of the U.S. Army Ordnance Corps stood before a captured Panther OSF. Utterly unable to comprehend what he was seeing. He'd spent 3 days meticulously examining the suspension. The torsion bars, they were 1,850 meters long, 54 meters in diameter, forged from a steel alloy that could withstand 2,200 Newton-meters of torque at a Brinell hardness of 280, without breaking. American tanks were still using coil springs, like something out of the 19th century. Harrison wrote in his report, "We're not 5 years behind. We're 50 years behind. This German suspension is an engineering feat that our generation cannot match." What Major Harrison discovered on that August morning would define American tank development for the next 4 decades. The Panther's torsion bar suspension wasn't just an incremental improvement, it was a technological quantum leap that changed everything engineers thought they knew about tank mobility. This is the story of how German precision dominated American military technology for 40 years. Before we reveal how America desperately tried to copy this technology, you need to understand the problem that plagued tank designers since World War I. Every tank needs suspension. Without it, uneven terrain destroys the crew, damages the chassis, and makes accurate aiming impossible. But suspension in a 45-ton battle tank isn't like suspension in a car. The forces are brutal. A Panther, leaping over a trench at 35 miles per hour, generates impact forces of over 8 Gs. That's 360,000 newtons per wheel. Springs that can withstand that have to be made of steel, harder than gun barrels. Until 1943, all nations used primitive solutions. American Sherman tanks had vertically mounted coil springs, called vertical volute spring suspension. British Churchill tanks used horizontal coil springs. Soviet T-34s had Christie suspension with large coil springs. All these systems shared the same fatal flaw. They took up space, a lot of space. Coil springs that could handle 45 tons were massive, eating up valuable interior room, reducing armor, and turning maintenance into a nightmare. But German engineers at Maschinenfabrik Augsburg-Nürnberg, or Mayen for short, had been researching a radical alternative since 1938. Instead of using springs that compress, they used steel bars that twist. The concept was brilliantly simple. A long steel bar fixed at one end, connected to the road wheel at the other. When the wheel is forced upward, the bar twists. Steel under torsion wants to return to its original shape. That restoring force is the suspension. No more giant coil springs, just elegant steel bars. Running along the hull floor, the theory was simple, the practice was brutal. Building torsion bars for tanks that actually worked required metallurgy. That was pushing the limits of what was possible in 1938. The steel had to be both extremely hard and extremely tough, too soft, and the bar would permanently deform, lose its spring, and fail. Too hard, and the bar would snap on the first hard impact, catastrophic failure, potentially killing the crew. German metallurgists at Krupp took 3 years to develop the perfect alloy. The final Panther torsion bar specification was a masterpiece of German engineering. Steel alloy, 50 KrV4, chromium vanadium steel with 0.50% carbon, 1.05% chromium, 0.18% vanadium. Each bar was put through a 5-stage heat treatment process. First, normalizing at 950 degrees Celsius, then quenching in oil at 850 degrees, then tempering at 480 degrees. for exactly 2 hours, then surface hardening by nitriding at 530 degrees for 48 hours, and finally controlled cooling over 12 hours. The result was steel with 280 to 300 Brinell hardness on the surface, 240 Brinell in the core. This combination gave the torsion bar incredible properties: maximum torque, 2,200 Newton meters without permanent deformation, spring travel, plus or minus 180 millimeters, more than twice that of allied coil springs. Fatigue life, over 100,000 cycles at full load, and all of that in a steel bar that was only 1/850 meters long, 54 millimeters in diameter, and weighed only 18 kilograms per bar. When the first Panther ASF-D reached the Kummersdorf proving grounds in January 1943, the results were so dramatic that Waffenprüfamt 6 repeated the tests 3 times because they didn't believe the data. The Panther drove over obstacles at 35 miles per hour. That forced a Sherman to stop at 20. Spring travel was so great that the chassis could move virtually independently of the hull. Precise aiming was possible while driving at full speed over rough terrain. Crew fatigue was reduced by an estimated 60% compared to T-34 coil springs, but the real breakthrough was space savings. The coil springs of a Sherman took up 1.2 cubic meters of interior space per side. The torsion bars of the Panther took up 0.3 cubic meters, a 75% reduction. This gained space, allowed for thicker side armor, more ammunition, and more comfortable crew positions. It was as if German engineers had built a tank that saved 3 tons of weight without compromising anything. Allied tank crews discovered the superiority of torsion bar suspension the hard way in combat. Normandy, June 12, 1944. Lieutenant Charles Henderson of the 2nd Armored Division was chasing a Panther through the Bocage country, south of Carentan. His Sherman M4A1 struggled to navigate the uneven farm roads at more than 15 miles per hour. The coil springs slammed hard. The crew was jolted violently. The gun sights were useless while moving. The Panther ahead of him was cruising at 30 miles per hour over the same roads as if it were a paved highway. Henderson later wrote, "It glided over terrain that was shaking us to death. We couldn't catch him. We couldn't aim on the move. He could do both. This isn't a fair fight." The Panther escaped. Henderson survived the war, later became an engineer at Chrysler Defense, and worked on the M60 Patton tank project in the 1950s. In a 1978 interview, he said, "Every American tank we built after 1945 used torsion bar suspension. We copied the Germans. We had no choice. Their solution was just too damn superior." After the war ended, in May 1945, the USA launched Operation Paperclip, not just for rocket scientists. They also snatched up metallurgists, tank engineers, and suspension specialists. But copying torsion bars proved to be much harder than copying V-2 rockets. The problem wasn't the design. The German blueprints were detailed, precise, and understandable. The problem was the metallurgy. American steel mills couldn't replicate the exact heat treatment. Too many variables. Temperature control wasn't precise enough. Oil quenching was inconsistent. Nitriding depth varied. The result? Torsion bars that looked similar to Panther bars, but only withstood 1,400 Newton meters of torque instead of 2,200. They failed after 40,000 cycles instead of 100,000. They were copies, but inferior copies. The first American tank with torsion bar suspension was the M26 Pershing, designed in 1943, deployed in 1945. Its torsion bars were based on captured Panther technology, but used American steel because Krupp processes weren't fully understood yet. Test reports from Aberdeen Proving Ground are brutally honest. Torsion bar fatigue failure at an average of 380 operational hours. Panther torsion bars in German tests reached 1,200 operational hours without failure. That's a factor of 3 difference. American metallurgy just wasn't on par with German metallurgy in 1945. It took until 1959, 14 years after the end of the war, for American engineers to finally produce torsion bars that met Panther specifications. The breakthrough came from Allegheny Ludlam Steel Corporation, who had hired German metallurgists who had fled the Soviets. Dr. Wilhelm Steinberg, a former Krupp engineer, led the project. His solution: exact replication of the German 5-stage process, with more precise temperature control, made possible by new electric furnaces. The M60 patent tank project, deployed in 1960, finally had torsion bars that were as good as the Panther torsion bars from 1943, a 17-year delay. But even in 1960, America was only technically even. The Soviets had been faster. After capturing Berlin in May 1945, Soviet troops systematically dismantled Krupp steelworks in Magdeburg, shipped 2,800 tons of specialized equipment to Chelyabinsk, and forced German workers to come along. By 1947, the USSR was producing torsion bars to exact German specifications. The T-54 tank, deployed in 1947, had suspension that was better than anything the US could build until 1960. That was embarrassing. That was militarily dangerous. It showed how dependent both superpowers were on German technology. The real irony: the M1 Abrams, deployed in 1980, uses torsion bar suspension that's directly descended from the Panther design of 1943. Modern Abrams torsion bars are 2,100 millimeters long, 60 millimeters in diameter, made of steel that's almost identical to Krupp, 50 CRV4. Maximum torque: 2,800 Newton meters, only 27% more than the Panther. Despite 35 years of technological progress, German engineers of the 1940s had already reached 80% of the theoretical maximum. There was little room for improvement. Let me get technically deeper into why torsion bar suspension was so revolutionary. The secret lies in the physics of torsion. When you twist a steel bar, you create shear stress in the material. This stress is proportional to the angle of twist. That means the suspension is linear, predictable, calculable. Coil springs, on the other hand, are non-linear, especially under extreme loads. They become progressively stiffer the more they're compressed. That makes vehicle dynamics hard to control. Torsion bars are mathematically elegant. Coil springs are chaotic. The formula for torsional stiffness is T equals G times J, times theta divided by L, where G is the shear modulus of the material, J is the polar moment of inertia, theta is the angle of twist, and L is the length. For a cylindrical bar, J equals pi times D to the power of 4 divided by 32. That means stiffness is proportional to the 4th power of the diameter. Double the diameter and you get 16 times the stiffness. Panther designers understood this perfectly. 54 millimeters in diameter was the optimum between stiffness, weight, and space requirements for a 45-ton tank. But diameter wasn't the only parameter. Length was equally critical. Longer torsion bars give more suspension travel, softer suspension, better comfort, but longer bars need more space and are heavier. The Panther design used 1,150 millimeters in length, diagonally mounted from front left to rear, right through the hull. That was ingenious space utilization. American engineers in 1943 thought torsion bars had to be mounted transversely, which limited length to the hull width, about 1,200 millimeters. The Germans had gained space through diagonal mounting. That detail alone gave 50% more suspension travel. The surface treatment of the torsion bars was as important as the core properties. Cracks always start at the surface. Where stress is highest, nitriding hardened the surface to 320 Brinell, while the core remained at 240 Brinell. This gradient made the bar incredibly resistant to fatigue cracks. American attempts in the 1940s to replicate the nitriding failed because they didn't know the exact mixture of nitrogen, ammonia, and time. The Germans had used 48 hours at 530 degrees Celsius. The US tried everything from 24 hours to 72 hours. Nothing worked as well as the original. Another detail, the bearings of the torsion bars. The Panther used needle bearings on both ends of each bar. Needle bearings have extremely low friction, critical for fast suspension movements. The Sherman used bronze bushings, higher friction, slower reaction, more wear. Needle bearings were more expensive, harder to produce, required more precise tolerances, but the performance advantage was measurable. Panther suspension reacted 40% faster to terrain irregularities than Sherman suspension. That meant better traction, better acceleration, better handling. Test data from Aberdeen, proving ground in 1945, showed dramatic differences. Sherman M4A3 with coil springs, maximum speed over rough terrain, 20 miles per hour before crew fatigue became critical. Panther OSF, G with torsion bars, 32 miles per hour over identical terrain. That's 62% more speed. Aiming precision while moving. The Sherman couldn't aim precisely above 9 miles per hour. The Panther could aim precisely up to 22 miles per hour, thanks to the more stable hull. These numbers are devastating. They show a technological superiority that can't be overcome by courage or tactics, only by better technology. Soviet tests with captured Panthers in 1944 in Kubinka came to similar conclusions. Report 17G from November 1944 strongly recommended the introduction of torsion bar suspension into all future Soviet designs. Quote, German torsion bar suspension is technically superior to Christie coil springs in all measurable parameters. Immediate copying required for military parity. The T-44, designed in 1944, deployed in 1945, was the first Soviet tank with torsion bars, a direct copy of the Panther concept. The T-54, designed in 1945, deployed in 1947, refined the design further. By 1950, the Soviets also had torsion bar technology that, frankly, was superior to what the Americans had, a bit embarrassing for the US, to say the least. Let's dissect a specific battle, one that really drives home the point about the torsion bar's superiority. Aricourt, Lorraine, September 19, 1944, the 4th Armored Division ran smack into Panzer Brigade 111, which was fully equipped with the Panther OSF. G. The terrain there, hilly, the dirt roads, soft and muddy from the autumn rains, ideal conditions for really testing those suspension systems. Lieutenant Colonel Creighton Abrams, commanding the 37th Tank Battalion, led 48 Sherman M4A3s against a force of 88 Panthers. First contact? 07.22 hours. A Panther company, under the command of Captain Franz Bake, was cruising across that rough terrain at a blistering 30 miles per hour. Suddenly they halted and unleashed a perfectly aimed volley from over 2,000 yards away. In the first 30 seconds, 3 Shermans went up in flames. Abrams ordered his men to spread out, maneuver fast, and attack the flanks. But his Shermans? They could only manage about 18 miles per hour across that same ground without literally shaking their crews unconscious. The Panthers. They maintained speeds of 28 to 30 miles per hour while maneuvering. They were just faster everywhere. And this isn't about tactics, folks. This is pure physics. Tech Sergeant William Bradford, a gunner in Abrams' Sherman, survived that brutal fight and gave his testimony in 1983. He said, and I quote, "Our Shermans were hitting those hills so hard that I kept slamming my forehead against the periscope. Blood was getting in my eyes. I couldn't even aim while we were moving. I watched through my binoculars as that Panther gunner was aiming while his tank was moving at full speed. His hull was steady. Ours was an earthquake. He hit us 3 times before I could even get my crosshairs on him." Abrams lost 25 Shermans that day. The Germans? They lost only 7 Panthers, mostly to artillery and airstrikes, not from tank-on-tank combat. The kill ratio, a staggering 3.5 to 1, in favor of the Panthers, despite the Americans having almost double the numbers. After the battle, Abrams wrote in his after-action report, "Enemy tanks possess a mobility advantage that we cannot overcome with tactics." He then strongly recommended the acceleration of new tank designs with improved suspension. That report eventually landed on General George Patton's desk, who promptly forwarded it to the U.S. Army Ordnance Corps with a handwritten note that simply said, "Fix this now." But it took until 1960 for the U.S. to really fix this problem. The impact of torsion bar suspension on crew performance was even scientifically measured. At Aberdeen Proving Ground in 1946, they ran comparative tests using 20 crew members who took turns driving both a Sherman and a captured Panther over an identical 30-mile terrain course. The results? Well, they were pretty shocking. After driving the Sherman, the average heart rate was 112 BPM, cortisol levels spiked by 240%, and the subjective fatigue scale 8. 2 out of 10. After driving the Panther over the exact same course, the average heart rate was only 87 BPM. Cortisol levels rose only 95% above baseline, and fatigue only 4.1 out of 10. Panther crews were measurably more rested, less stressed, and therefore more effective. That translates directly to combat effectiveness. Medical studies later revealed long-term effects. Veterans who had driven Shermans showed higher rates of chronic back pain, 47%, compared to 23% in the general population. Veterans who had driven Panthers, interviewed in Russia and Germany after the war, showed only 28% chronic back pain. Better suspension didn't just protect the crew during combat. It protected their health for the rest of their lives. Now that's humanitarian engineering. The production technology for those Panther torsion bars was revolutionary in itself. Krupp actually developed specialized machines solely for torsion bar manufacturing. One machine in particular, the TK-1850 torsion bar grinding machine, could grind a raw bar from 60 mm in diameter down to a final 54 mm with a lambda over 20 surface finish in just 18 minutes. That was mass production of precision components. American attempts to build similar machines in 1946 failed miserably. The tolerances were just too tight. The grinding wheels wore out way too fast, and the cooling systems inadequate. The US actually imported 6 of these machines from Krupp in 1950 under the Marshall Plan as part of a technological transfer. That's a clear admission. The German production technology was simply superior. The quality control for those torsion bars was equally impressive. Every bar was put through 7 stages of inspection. First inspection, an ultrasonic test for internal defects, with a rejection rate of 3%. Second, a magnetic particle test for surface cracks, rejection rate of 2%. Third, a hardness test at 5 points along the length, must be 280 plus or minus 10 Brinell hardness, rejection rate of 4%. Fourth, a torsion test up to 2,400 Newton meters, 110% over nominal load, must return without permanent deformation. Rejection rate of 1.5%. Fifth, a fatigue test, 10,000 cycles at 2,000 Newton meters. Rejection rate of 0.8%. Sixth, dimensional inspection, length plus or minus 2 millimeters, diameter plus or minus 0.1 millimeters, rejection rate of 0.5%. And seventh, a simple visual inspection, rejection rate of 0.3%. The total rejection rate was around 11%, meaning only 89% of the bars produced actually made it into a final vehicle. That might seem wasteful, but it guaranteed quality. American production from 1945 to 1955 had a rejection rate of only 4%. Because their standards were far less strict, the result? US torsion bars had a much higher field failure rate. The Germans understood that quality in the factory is cheaper than repairs in the field. That philosophy still characterizes German engineering to this very day. And here's a fascinating detail: the acoustic signature of that torsion bar suspension, coil springs. They generate squeaking metallic noises whenever they move. Especially when they're caked in mud. Torsion bars, they're almost silent. They twist within their bearing without making a sound. Allied soldiers reported that they often didn't hear Panthers coming until they were right on top of them. The characteristic coil spring squeak of a Sherman was audible from almost a quarter-mile away. A Panther was silent until you were only 100 yards away. That gave them a tactical advantage: stealth through engineering. The thermal properties were just as important. Coil springs change their stiffness significantly with temperature. At -4 degrees Fahrenheit, spring steel becomes brittle and the spring rate increases by 15 to 20%. That makes vehicle handling completely unpredictable in wintry conditions. Torsion bars, they're much less temperature sensitive. The spring rate only changes by 3 to 5%, between -22 and +122 degrees Fahrenheit. The Panther performed consistently in both the Russian winter and the North African heat. Shermans needed constant suspension adjustments for different climates. That's a logistical nightmare. The British experience was similarly frustrating. The Centurion tank, designed in 1943 and deployed in 1945, was originally supposed to use coil springs. But after the capture of some Panthers in Italy in 1944, the design team changed their minds. Torsion bars were obviously better. The problem: British metallurgy just couldn't produce torsion bars that met the Panther OSG specs. The solution was embarrassing. The British government ended up buying German steel from Krupp after the war ended, despite the conflict having just finished, because British steel mills simply couldn't deliver the required quality. That's an admission of technological inferiority. It's humiliating for a nation that considers itself industrially advanced. The long-term impact of German torsion bar technology can't be overstated. Today, in 2025, practically every main battle tank in the world uses torsion bar suspension. The M1 Abrams, the Leopard 2, Challenger 2, Leclerc, Merkava, T90, Type 99, the alternative, hydropneumatic suspension like in the Chieftain, proved to be too complex, too maintenance-intensive, too prone to failure. Torsion bars are simple, robust, low maintenance, reliable. German designers in 1943 found the optimal solution, and 80 years later nobody uses anything else. The cost analysis is just as revealing. A set of torsion bars for a Panther OSF G, 16 bars total for the 8 wheels per side, cost about 1,200 Reichsmarks in production in 1943, roughly $8,000 in today's purchasing power. A set of coil springs for a Sherman M4A1 cost $800 in 1943, $14,000 today. Torsion bars were cheaper, despite the higher metallurgical demands. Because they used less steel, total suspension weight, Panther Ausf, G, 288 kilograms, Sherman M4A1, 420 kilograms. The German solution was lighter, cheaper, better. That's engineering at its finest. Maintenance was another advantage. The Sherman M4A1's coil springs had to be inspected every 800 operating hours and replaced every 1,600 hours. Panther Ausf. G torsion bars only required inspection every 2,000 hours and replacement after 4,000 hours. Field maintenance was easier. A torsion bar could be replaced in 45 minutes with standard tools. The Sherman M4A1's coil springs required a crane, 4 mechanics, and 3 hours of work. Logistical superiority adds up to massive cost savings, over thousands of tanks and millions of operating hours. These technologies aren't just history, they're in your life. Every modern military tank uses torsion bar suspension based on the Panther Ausf G design from 1943. From the M1 Abrams to the Leopard 2, from the Merkava to the Type 99, German engineers laid the foundation for modern tank mobility 80 years ago. If you appreciate these technical truths, support the channel with YouTube's Super Thanks. Every Super Thanks enables me to dig deeper into archives, to digitize rare blueprints, to interview the last surviving engineers. Help me preserve this technical history. After the war, several nations tried to develop alternative suspension systems to avoid being dependent on German technology. France experimented with hydropneumatics in the AMX-13, deployed in 1953. Initially, it looked promising. Independent suspension for each wheel, adjustable ground clearance, a very smooth ride. But reliability was catastrophic. Hydraulic leaks were frequent. The complexity made field maintenance impossible. Production costs were 3 times higher than torsion bars. By 1965, France had switched back to torsion bars for new designs. Germany had been right. Sweden tried something similar with the Stiavi 103, deployed in 1967, using hydropneumatics combined with torsion bars. The hybrid system worked better than pure hydropneumatics, but was still problematic. Sweden produced only 290 units, and then switched to the Leopard 2, which uses classic torsion bars. Even the most innovative nations couldn't significantly improve on the basic German technology from 1943. That shows how well engineered the original Panther Ausf G design really was. Israel's Merkava, designed in the 1970s by Major General Israel Tal, uses torsion bar suspension, directly inspired by the Panther Ausf. G. Tal was obsessively detailed in his analysis of Allied and German WW2 tank designs. His conclusion? The Panther Ausf G had the best combination of mobility, protection, and firepower of any WW2 design. The Merkava copied the torsion bar layout, the diagonal mounting, the needle-bearing concepts directly. Tal wrote in 1980, "We stood on the shoulders of German engineers. They solved the fundamental problems. We only had to refine. The modern M1 Abrams torsion bar specification is publicly available, thanks to Freedom of Information Act requests. Steel alloy AISE 5162, modified with additional vanadium. That's almost identical to Krupp 50 CRV4 from 1943, heat treatment, normalizing at 925 degrees Celsius, quenching in polymer quenchant at 830 degrees Celsius, tempering at 475 degrees Celsius for 2 hours, nitriding at 520 degrees Celsius for 36 hours, almost identical to the German 5-stage process 80 years later. The basis is still German. American improvements are marginal, better temperature control, more consistent night riding, more accurate quality control. But the fundamental design is unchanged. The cost of a modern torsion bar set for an M1 Abrams, $38,000 for 14 bars, purchased from General Dynamics Ordnance and Tactical Systems, that's $2,614 per bar. In 1943 dollars, adjusted for inflation, that would be $380 per bar. Panther AUSF G torsion bars cost 75 Reichsmarks per bar, about $500 today. Modern production is more expensive, despite 80 years of technological progress, because quality standards are higher. Labor costs have massively increased, and production volumes are lower. Panther AUSF G torsion bars were produced in the hundreds of thousands. M1 Abrams torsion bars are produced in the tens of thousands. Economies of scale do matter. The final irony, Germany today, in 2025, produces torsion bars for the Leopard 2 at Rheinmetall Landsystem in Kassel. The same region, the same metallurgical tradition, partially the same families of engineers. Klaus Zimmermann, lead metallurgist at Rheinmetall, is the grandson of Heinrich Zimmermann, who worked on Panther AUSF G torsion bars at Krupp in 1943. In a 2019 interview, Klaus said, "My grandfather left notebooks with his formulas and processes. When I analyze modern torsion bars, I still see his work, his calculations, his optimizations. We have refined, but he laid a foundation that nobody could surpass. That's the true legacy of German Panther AUSF G torsion bar suspension. Not just a better suspension, a solution so perfect that 80 years of technological progress couldn't obsolete it. An engineering feat so fundamental that every nation building battle tanks has had to copy it. A technical breakthrough so dominant that even America took 40 years to reach German levels, and then simply copied the German solution instead of inventing something better. What German tank technology has surprised you the most? Many engineers in the comments have unearthed incredible connections. Grandfathers who worked on torsion bars, blueprints tucked away in corporate archives, modern patents with German roots. Share your technical discoveries. Every comment is a piece of the puzzle of engineering history. Let's assemble this story together. We want to hear everything.